kind of want to learn something about the audience. Who here does some language design? Handful of people. All right. Any of you not like have a PhD? Oh, sorry, of the language designers. Yes, actually, I want to know that too. So that's good to hit those hands. But of the language designers, who doesn't have a PhD? Oh, almost everyone. That's surprising. All right. Good to know. And now I know how much industry people there's in the audience. Okay. I am Ross Tate. I'm a professor at Cornell University. I also advise multiple languages on sort of how to improve their type systems. This is somewhat of an unusual setup, so I figured I should give a background. Okay, so first of all, I went to Cal Poly San Luis Obispo as an undergrad. This is a completely industry-oriented school. I am, I think, the only person in my major that went to grad school my year. So I never planned on going to grad school. I used to make video games, so, but then I went to UC San Diego because of a bunch of pressure from faculty, and then interned at Microsoft Research, and then now I'm a professor at Cornell. All right, I studied to make video games, so I actually worked on Activision's internal programming language that they use to script their games. And this was as an intern, but then they hired me back later on to redesign their language. Later on, I did some research on language design, and the Ceylon team contacted me about how they could apply that research to their language. And then the Kotlin team did the same thing. And just recently, like very recently, I started working with the Java team, but we haven't actually got anything done yet. So I'm working on bridging this gap between academia and industry, trying to help these people understand what research there is out there they can use, and also help the academics understand what the needs of industry are. So my goal in all this is to sort of make the industry languages better. Now, what's important to note is that I'm not saying make a industry language better. I don't have my own language. I actually want to make sort of many of them better. And also, better is in quotes. That's because it's not clear what better means. Right? We don't really have a good way to evaluate things like productivity or stuff like that. And although I used to be a web developer, did so before JavaScript was a really big thing. So I keep myself in touch, but this is something different between doing things every day and doing things just once in a while to keep yourself up to date. So rather than me making the call, I work with other people and help them, or who make the call and help them work that through. So my approach is to help industry language designers create the language that they envision. Right? If you want your language to look like this, or act like this, or interact like this, you have an idea of how to go about doing that, but there's a lot of details to work out. There's a lot of technologies you have to introduce. There's just a lot of open problems. And so I help them navigate either the open problem, or either the existing problems and let them know solutions exist already, or the open problems and come up with new solutions for them. So I just said I don't push my own vision, but I have this one principle I've seen sort of hold throughout all my interactions, which is this idea of predictability. So predictability is the ability for a program, or is the degree to which a programmer can predict what their language will do. This is something like, I can predict what if this type of code I'm going to write is going to type check, or I can predict if the library I'm going to use is going to be usable, or I can predict if this part of my code is going to perform well. If things go better than your predictions, that's great, but you at least want to know sort of the minimum ground so you can plan ahead. So predictability isn't a mathematical property of languages, right? I can't formalize this in any mathematical way. This is a human property. This is about how people work with languages. And so this is something that I'm trying to see how we can bring sort of into mathematics. So can I try to abstract these things and say, okay, this pattern tends to be more predictable, or this behavior helps things out. And let me give you an example. So the Kotlin team, back when, was like, Ross, we want to be interoperable with Java, but we don't like wildcards. And I imagine a number of you can agree with that sentiment. But wildcards have a use. They encode something called variance, and variance is very prevalent across our programs. So what is variance? Well, an example is an iterator of integers can safely be used as an iterator of numbers. Right? If I'm getting numbers out of it, I don't mind if those happen to all be integers. That's fine. It's just a coincidence. Another example is I'm only putting things into this list. And so I don't have to worry about whether that's a list of integers or a list of numbers or a list of objects. Any of those is fine so long as I can put integers into it. So these are both uses of variance, or concepts of variance. The top is best represented using declaration site variance. That is, when you declare iterator, from this declaration, you can see that it has this property. because you can only get these values out of it. And the bottom is a use-site variance. It's not a property of all lists, it's a property of how you're using this particular list. So wildcards encode use-site variance. But in C# later, it started using declaration site variance. And from this experience, people have sort of said that this one is, if you can only have one of these two, this is the one to use. It's just, this one has a lot of syntax, and it can be overburdensome, whereas this one is easier for people to learn. So the Kotlin people wanted to use this, but they needed to interact with Java, and use-site variance is more expressive than declaration site variance. And the thing to note also is that both of these are useful. They cover different kinds of situations, so ideally we could have both. So the question that came up was basically, how do we combine these kinds of variants? So let's give it a little more detail. So declaration site variance looks like this. You say this is the interface of iterable that works for any E, and it's out E. You get E's out of this thing. And this is use-site variance. This particular list is something I'm going to put integers into. So what goes here could be a list of integers or a list of objects, that's fine, but this tells you how you're going to use this particular list. So there's sort of an obvious way to combine these, just like let people do both that and that. But the question that comes up is, what is an iterable I could put numbers into? Now there's more complex examples that are not quite so obvious or quite so perplexing, but a bunch of people have actually worked on formalizing this already. So I went through the literature and saw that there were all these formalizations, but they didn't agree with each other. Some of them said this should be the case, some of them said this should be the case, and it wasn't clear which one is correct. So rather than designing a language and telling programmers, here's how this language works, I flipped it around. I said, I want to figure out what will work for programmers. What is the most predictable to them? And so I came up with a sort of methodology for a simple predictability study. So the idea is, write a bunch of programs, because validity depends on sort of the question in mind. So this program will type check if you interpret iterator this way versus this way, stuff like that. And then give these programs to people that know the features at hand, right? So they have backgrounds. We want to exploit that background, so let's see what's understandable to those people. And ask them which programs they think should be valid. But don't tell them any rules, right? They just rely on their intuitions or their prior experience and just say, what do you think makes sense here? And then collect all those answers and see what patterns you get. Okay, so I did this for this combined site variance thing. And these are the results. People didn't agree with each other. You give the same program to somebody, and they'd say, this should work, and the same program to another person, and they say, this doesn't work, or shouldn't work. But what's more interesting is that they didn't agree with themselves. So I actually would give the program and just rename things, and give them that program back. They didn't know I did this, but, and they would say, okay, that one should be accepted, and that one should not be. Just the change of names changed what they thought should work. And the reason is that names sort of imply some semantics. But type theory doesn't know what these names mean, and so I can't rely on that kind of semantics that's in their head. I have to have something that works for all names. And so I asked a different question, because I was afraid that if I made some design, no matter what, it's going to confuse somebody. And I don't want to do that. So the question I asked was, does iterable in number make sense? Right? I can only get values out of iterable, so why does it make sense to say this iterable I could put numbers into? So my question is, or my answer to that is no. I don't understand why anybody would ever use that type. And so I came up with mixed site variance. And the core idea of mixed site variance is that you reject these use sites that sort of contradict or oppose the corresponding declaration sites, right? So we have an iterable in where iterable is out. That's a contradiction. You can weaken, and that's fine, but just opposites just don't make sense. And what we found, looking back through that analysis, is that this is actually precisely the cases where people agreed. Everyone agreed on the examples that mixed site variance allowed. So rather than saying, let's allow all types and give a semantics to all types, let's just restrict the types to just the ones that we think make sense. And it seems like this worked in practice. And interestingly, it went through all the formalisms, including some I had made up just to try to consider more options, and they all agreed exactly on these cases as well. And this might imply this, right? It might be that everybody says, okay, well, I have this intuition for how these programs work. That intuition, at some abstract level, corresponds to some mathematical model. And so no matter which intuition you use, because they all agree, you get the same answer. Now, you might be saying, well, you're throwing out a bunch of types. Maybe those are the useful types, right? You're saying, I'm not allowing these programs. Maybe that's a problem. When we looked into it, basically actually has all the full expressiveness of combined side variance. The things like iterable in number don't really give you anything useful. So you can just stick with the subset and still have everything you want. Now, because this is both sort of predictable, usable, and also really easy to implement, right? Because you just say, syntactic check, don't like these, okay, same typing rules that we already know for everything else. And as a consequence, it was adopted by Kotlin, which makes sense. I mean, I designed it for them. But later on, Ceylon actually was trying to avoid having use-side variance, but they ran into a bunch of the uses of use-side variance that they wanted to have, and so they added it in the form of mixed-side variance. So this is an example of sort of looking to people first before coming up with a design. And in that way, trying to make design predictable for people, right? If they're already checked without them knowing what the rules are, that it gives them the same rules that they expect, we believe that should make it more predictable. So as another example, or I have a sort of this, I'm still debating this question, but if I want a language to be predictable, does it have to be decidable? And so I've asked this question many times, and one of the most common answers is, well, Java's undecidable. If you didn't know this, Java's undecidable. But people don't really run into that, right? Have you ever had a program not type checked because the type checker couldn't figure it out? Yes? What was it? Oh, really? Who was in the malicious user? So in practice, Java is decidable. Some people say decidability doesn't matter because in practice it's decidable. But the fact is, you still care about decidability. You care that it's decidable in practice. So the question is, why is it decidable in practice, right? How do I know I'm going to add some feature that people are going to use, and now it's not decidable, and it turns out also be not decidable in practice? So what I try to do whenever I have this kind of problem is say, well, let's look at how practice works. What are people doing in practice that makes it that the Java compiler can handle it? So I'll get into that in a bit, but first, it's time to crash the compiler. Okay, so here's some Java code. Oh, and it's not popping up. I crashed. Oh, I know what it is. It's because I'm in the wrong mode. Duplicate. There you go. Okay, so there's some Java code. It doesn't really make any sense. Right? There's these E's, these D's, these C's. E's and D's really don't do much, and C extend is a big, complicated thing. Let's not worry about that for a second. It's not supposed to make sense. And then we have this coerce thing, and it takes this C that's a C of X, and it returns it. And so the compiler has to ask, hey, is a C of X a D question mark super C of X? That's all it takes to type check this program. And so if oh no, I had it. Oops. There we go. So that's the compiler's answer. It's not a yes or no, it's just I really tried hard. But I couldn't figure it out. And what's concerning is things like gradual typing, which you kind of saw a bit in the last talk, tries to do these checks at runtime. So if these things are happening at runtime, you never know if runtime is going to suddenly crash your program because it can't figure out whether two types are subtypes of each other. Okay, so C# has solved this problem. Oops. Let's go back to extend mode. There we go. Oh, that's my baby. Project. C# has solved this problem. Sorry for the technical difficulties. There we go. So here's a C# program that kind of exhibits the same behavior. I'll go into why later. But we can actually start using it. So you can start, okay, it handles the classes, and you start typing things. And it goes, and then eventually it crashes. So C#, as I said, solved this problem, and yet it's still crashing. So why is that? Well, the solution C# uses is actually quite expensive. It has to, as it recurses through the program or through the subtyping, has to remember everything it looked at so far and check to see whether it's repeating itself. And that's just expensive, but IDEs need to be responsive, right? If you press dots, you don't want to wait. You get really annoyed if you have to wait for that thing to pop up. And so the IDE said, well, this thing's too expensive. Let's just not do that part and just hope for the best. And here I crashed its hopes. So not only do we want it to be citable, we actually want it to be efficient. We want it to be something that the IDE can implement easily. And that itself takes a whole bunch of work I'm not going to go into today. But let's look at why these problems happen. So here's a class. And that's the one from that Java program. Again, don't worry about understanding it. And here's the subtyping rule that this Java program had to check. So what Java does, it says, well, here's a C and a D. They're not the same class. So let's use inheritance. Now we have two Ds. And then the rules for wildcards say, there's this wildcard. If I can instantiate it over here with, say, that, such that it satisfies this super CX constraint, that is, it's a super type of C of X, then this type checks. So it recurses and says, okay, well, now is a C of X a subtype of D question mark super CEX, or in other words, is D question mark super CEX a supertype of CX? And then it says, okay, well, C's and D's and this apply inheritance. And then this is instantiation again. And so we get to there. And the thing to note is that this is basically the exact same thing we started with, except now we've exchanged X with E of X. And you can just do this forever. So eventually you get D, E, X, and yeah, it just never finishes. So this is actually an infinite proof of subtyping. That is, if I'm allowed to prove forever, I can show these are subtypes. And so the Java type checker is trying to prove something forever, which is why it crashes. Now you might say, okay, I don't care. This thing is completely contrived. And I'll get to that in a second. But first I need to take a step back. Okay, so the Ceylon team told me actually is one of their design philosophies that they want to be decidable before I even talked to them about predictability. So they care particularly about that stuff. But they also have this other goal that they want to have type safe equality. That is, if I say X equals Y, I actually know that Ceylon will check that X and Y have this, or similar types, and those types have a well-defined equality on them. You may have run into this bug in the past. But the problem is lists. It makes sense to equate two lists if their elements make sense to equate. So there's sort of this condition going on there. And expressing that condition using traditional methods is really difficult. It's known as the binary method problem, and it came up with a solution. So this thing, so in Ceylon, lists are what's called covariant, so you can only, or invariant, or sorry, immutable, you can only get values out of it. And it's saying lists are equatable with other lists whose elements are equatable with these elements. And this works, it actually solves the question. Lists of integers are equatable, and lists of functions are not equatable. So I could check the solution to them, and this was their answer. Now, I didn't make the slide. This is my student, Amin. Actually, is Ben Greenman here? Okay, he's my other student who worked on me on this project, who worked with me on this project. And Fabian made these awesome slides. So being the good researcher I am, after pouting a bunch about people hating my solution, I went eventually and asked them, why don't you like this? And they said, well, you're using these weird types. We don't understand these types. Well, they understood them, but they think they're weird. And I said, why is that? Well, there's no such thing as a list of equatables. Equatable is essentially something to say, this type is equatable. You don't hand around equatables. You don't put them in lists. You might put E's that are equatable in lists, but you don't put equatables themselves in lists. And I thought this was really interesting, right? This is, as a type theorist, I'm like, these are just types. You can do whatever the hell you want with them. And this solves your problem. In fact, they have yet to find a solution. But they still won't take this as a solution that I gave them. So I decided to formalize this intuition. Or we decided, I should say. So I came up with this idea of materials. Some examples are list, integer, comparator. These classes are classes you hand around, right? You say, I take a list, and I return a comparator. Or I take an integer, and this is a list of integers, right? You actually also use them as type arguments. Right? You can have, or sorry, there's field value return types. and you get lists of lists of lists of integers if you want. That all makes sense. But as we just talked about, you can't have lists of equatables. That doesn't make sense. And so what is equatable? Equatable is what I call a shape. Comparable, which is a more familiar example, is also a shape, right? The idea is that this is describing a type, not necessarily a value. And so these are used recursively in inheritance. That is, I have integer extends comparable integer. You probably have seen that. And similarly, I can sort a list of t's for any t that's comparable with itself. And these are, so shapes do not exhibit this behavior, and materials do not exhibit this behavior. Or that was my hypothesis. This is the idea that there's this material shape separation. That people naturally say that things are one or the other. And so what I guessed was that no class or interface is both a material and a shape. And to check this out, we analyzed 13.5 million lines of Java code. Basically everything we get our hold, all the generic Java code we get our hold on, from mining repos and all that stuff. And what did it say? Well, it said, you're right. There's not a single use in all these things, all this code, or not a single class or interface that's used both this way and this way. Everything falls cleanly into one category or the other. So this suggests that there's some sort of cognitive separation that's going on here, right? We don't realize we're doing this, but we happen to be always using one thing and everything one way or the other, even though we could conflate them if we wanted. And what does this give us? Well, for one, subtyping is decidable. In fact, it's decidable using a very naive algorithm, which is why, in practice, you don't run into these problems, because in practice, you're already doing this, and the naive algorithm that everyone's already using works. Okay, so can we learn anything from this? Well, if you notice, basically shapes aren't being used as types anywhere. They're just being used as type constraints. So if you make that separation, you say shapes are only type constraints and not types, then you get computable joins. So that means that if someone says, hey, I have an integer and a string, or if someone's asked the compiler, hey, I have an integer and a string, what's in common? And our system, the compiler would say, they're just both objects. There's not really much in common. But have you tried that in Java? Has anyone ever tried that in Java? Okay, so if you have something like question mark colon 5 hello, what Java will say is this is a comparable of something that's comparable of something that's comparable of something that's comparable of something that's comparable forever. And you say, I don't care. I don't care that's a comparable. I just don't need to know that's an object, because you don't use comparable as a type. You only use it as a type constraint. All right. Furthermore, this thing generalizes super well. So we proved that you could, it was basically trivially prove that we could do higher kinds. So if you wanted to add functors and monads, we'd be able to handle that and everything would still be decidable. Or at least subtyping still decidable. Other people, so Zhang et al. Proved that you can also do type classes with this. This solves a type class question for O, or with using U-site variants. So what I like about this is a situation where we took an undecidable problem, that is something that is proven to never be solvable, and we solved it. By incorporating the fact that this problem is not a mathematical problem, it's a human problem, right? We are the ones who care about this. We want to be able to program, and that's all we care about. So if we incorporate the human factor, that this sort of cognitive separation, we can solve the problem. And we can solve many other problems as well using that. And we're actually still exploring applications of this. And also, this is in language specific. It's already been used, explored in multiple languages. Ceylon team, for example, ran this on their repo as well and found the same thing. Actually, no, they found one counterexample, and they were already arguing about why they didn't like this design. So I gave them this, and like, okay, we'll just throw that out. It was really easy to change one to the other, so they just changed it. Okay, how am I doing on time? What? Okay, good. So questions first. Any questions about how you might do this with your language? No? So what I'm hoping is that people will sort of apply this idea to their own languages, that maybe not this, right? Maybe your language doesn't have generics. But this idea of, well, I have to make the design choice, rather than me making the design choice, let's ask the programmers what they expect. And do it in this sort of very concrete way. Here's a program, does this work or not? Here's a program, what does this do? And get all those answers and see if there's a pattern across those answers. In this case, the pattern was it was quite simple. There's a subset that everyone agreed on. But in other cases, there might be more complicated, right? You might have 90%, 10%, and you can make that choice yourself. Just, you can see what your philosophy suggests should be done in that situation. Yes?
I actually use Kotlin in production. I'm still trying to wrap my head around equatable of a generic of E rather than E being an extension of equatable. I guess that's the solution. So can you go a little bit deeper on that?
So I'm trying to remember what they did because I remember we talked about it. And I haven't actually looked at what is the difference when you collaborate with people. There's a difference between what they say we're going to do and what they actually do. So I haven't checked what they actually do yet. But it sounds like they say foo extends to equatable foo. Okay, and that's what Java and all those things do. Is that okay? So why do they do that rather than foo extends equatable? Is that the question?
Yeah. So the idea is that what is the difference between the boxing of the type inside equatable versus the type actually implementing the equatable itself? At least on the grammar, that was the suggestion.
Okay, so the difficulty. So there's two answers to this question. One is if you do standard inheritance and you say here's an foo extends equatable, just equatable. You don't know what's equatable to, right? Because equatable has an equals method and it says I take say object or something like that. And so if you want type space equality, you want to know, no, I'm just equatable, I'm equatable to these things. The other answer is that if you apply this stuff, you can basically actually, so a further study it is, we found that everybody who uses shapes always uses this form. It's always foo extends foo, or foo extends equatable foo. So you might as well specialize your syntax and say, well, how about foo satisfies equatable, right? And then, well, whenever that's done, it just figures out, well, that means that it's equatable with foo. And same with all your constraints. So you're getting rid of all that redundancy in your programs. That makes it clearer to programmers that these are separate concepts. And so when they have behavior or when they do something that maybe tries to contradict that, they're not surprised by it. Does that answer your question?
Oh, yeah. Really insightful. Thank you.
No problem.
I'm just trying to understand this. So materials are like first order and shapes are second order. It's like, so materials are sets of values and shapes are sets of sets?
Sets of types, yeah, yeah. So materials
yeah,
says this value is a thing that contains a bunch of values, right? Where the shape says this type is something that can be equated
so it's
with
like
itself.
First order logic and second order logic.
In some degree, yeah, yes. I see what you're saying. More questions? If not, I have more fun stuff we can do. But there's one. Oh, you're gonna pick on me now.
Yeah, I was thinking that actually it's a very nice result that you have separated the materials and shapes and achieved this huge reduction in complexity. And the funny thing is that this goes along with an increase in complexity because you have put together the declaration side and the use side variants, and that seems to be less of a cost. Somehow you can just wrap up a lot of use side declarations into the declaration side, so you won't have to repeat it all the places where you would probably use it. And it's basically like it's a semantic simplification because the syntax doesn't get much simpler because you say in and out, you know, it's not that different from question mark extends and question mark super.
There is value to that actually, but go on, sorry.
Yeah, but I think it's a really interesting distinction between the materials and shapes here. And I'm not quite sure if you could give a few more words on how that would help you get the computable joins.
Okay. So with computable joins, the question is, so say I have integer and string. So what happens is if you get rid of shapes, so you say these aren't types anymore. It's not finite, but you can actually walk up and sort of there's a finite number of principal instantiations of all prior classes. So you could say, okay, integer is also serializable, and string is also serializable. So actually, we might say serializable if you did it that way. But because there's no recursion anymore, that's taken out of the picture, and it's just sort of a finite number of steps you have to take and try out, and then once you've done those steps, you get the answer. So what's important is by taking these out types, there's no longer recursion in the process. There's a shallow recursion, but not these infinite recursions. Any more questions? Oh, okay. So now let's have some fun and let's just break a bunch of things. So I don't have time to sort of go into more things I'm fixing. These are actually old results. But we can break some things and give you some idea of what either we're working on or have worked on. Okay, so actually we'll start with the thing that actually got me into this entire field. So I was teaching a class, it's a programming language class where everyone learns a variety of programming languages. But the first thing, so what I wanted to do was have them implement a stat solver, a naive stat solver in every language, to see that different languages have different pros and cons. And so I had them do it in Java because they already knew Java. And so this students wrote this code. They said, okay, well, stat solvers have these variables. As I'm solving, those variables get values. And at the end, I have to figure out, well, what are all the variables, true variables, what are all the false variables. So I just gave an add to method and said add to the appropriate list. Right, if you're true, add to trues. If you add yourself to trues, if you're false, add yourself to false. And so the way to implement this method is this. Right? Depending on what value is, if value is true, then for the trues list or the falses list, add this variable to that list. This looks good, right? Okay, so the Java compiler rejects this. And you're like, why? This is like super obviously true. And according to the Java like typing rules, this is correct. And so my student obviously was like, what the hell is going on? And they came up, talked to me, and we looked at this. And so I dug through sort of the documentation stuff, or like the compiler documentation. And what they do is they say, well, question mark super is really hard. Like, so with the material stuff that we did, now this becomes doable. But before, without that stuff, it is actually really, really hard to do question mark super well. And so whenever they have the situation where they have these sort of question mark colon, these in general can have different types, right? One could be string and one could be integer, and you have to figure out a way to combine those types. And so they say, well, if either of those types has question mark super, we're just going to ignore that. We're just going to treat it as a list of question mark. And so it turns both of these into a list of question mark, which is sound, right? It's for getting this extra information. And then says, okay, well, I have these two lists of question marks. That's a list of question mark. And then I try to add a variable to this, and it says, well, I don't know what this question mark is, right? It could be anything. It could be an integer. And we're like, well, no, it's a variable. So this is fine. So the material stuff actually solves this problem. But it's interesting to see that there actually are examples where decidability does affect people. In this case, it was an easy fix. You make an if, and you do it in two separate branches so that the compiler isn't trying to do a join algorithm anymore. But that fix is not always easy. All right, another example. What does this do? Like, for my student, well, usually it's not integer to that value of 5. It's like, give me an integer from this list. And this is something that happens in JUnit. This is assert equals, right, and say, check that they're the same text, or the same value. So my students have to write this all the time. Anybody know what this does?
It says there's an overload for long and another overload for object, and both of them
Yeah.
doesn't know how to solve it.
It says it's ambiguous, so it rejects this code. And this, as you said, the two situations are, it can't tell whether this is two integers or two objects, right? Because integers have implicit conversion, or because integers can be converted to objects through the wrapping, and vice versa. Or sorry, ints can be turned to integers, and integers can be turned to ints. And doesn't know which way it's supposed to do. Of course, we know that doesn't matter. They're going to get the same answer anyway, but it doesn't know that. So it's ambiguous. Okay, let's make things worse. So here's, okay, I mean, you can actually implement this, but I'm being lazy and just putting null there. So singleton, here's some crazy mess. Unfortunately, I had to simplify it so that fits on the slide, so it doesn't make any sense. But understand that this, basically what's important is that it's a generic method that just says I need comparable things. And then here are a bunch of things that are just overloadings, right? It's saying, okay, well, what's the name of the type of this value? Okay, anybody know what this does? Okay, I'm just having fun now, so. Anybody know what this does? So first it's filling in the type arguments, right? It's saying, well, it's a singleton of something. I'll figure out what something is. It's a foo, and then that's going to be a foo of something, and I'll figure out what that something is. And then it gives you and then it returns some string. Guesses. How about somebody take guesses? Nobody's willing to take this. All right, well, I'll jump to the answer. It returns comparable if it wants. It returns string if it wants. It returns integer if it wants. It even returns calendar if it wants. Even though there's no calendar anywhere in here, it actually can say that, hey, this is a calendar. So what this setup does actually says, okay, well, type argument inference is going to sort of make guesses as what these types are. It is allowed to guess anything that makes this type check. And so depending on what it says, hey, this should be this type, this should be this type, it then does a different overloading depending on what types it's tried out. So Java, have you never seen this slide before? And I asked you, I forgot to ask you before this. Does Java's type checker affect your semantics? And probably everyone would have said no, but the answer is yes. So how a type checker code actually can change how your code runs. All right, another problem. Okay, so here we have singleton. There's that singleton listing again. And then we add 5 to it. Does this work? Does Java type check this? You say no, or you say yes? Everyone's like now very scared to say anything. Okay, so the answer is yes. Java typechecker does handle this. And the Java specification handles this as well. What about this? So what about the specification? What does the specification say? So according to the spec, this is valid, right? Because I can infer any type, say this is a list of whatever I want. So I can say this is a list of objects, right? I can do that. It's the same thing as I did up there. But a type checker fails to do that. And the reason is that inference in Java, and actually in C# and most of these things, uses the return type. It says, well, I know this is supposed to be a list of objects, so I'll use that information to figure out how to infer this. But here, I took that information away. I just, inlined the variable, but now that type is gone, and it can't figure that out. So it says, well, this is a string, and I'm just going to use that as my guess. And then it adds 5 to it, like, oh, I guess I was wrong, crash. Well, not crash, but like error. Yeah, so you can say brackets, objects, and make it explicit if you want. All right, so gradual typing, you've seen some sense of this before. The gradual typing is the idea that you can make things dynamic if you want. Okay, so there's an equals method from C#. So C# has dynamic, and here's equals 0, 0. What does this do in C#? C# program is here. Returns true or false. What do you think? So remember that objects, or it has to wrap things up, right? So it turns zeros into objects, and then what does it do? Reference equality. So you get different answers. Well, it depends if it tries to do caching and stuff like that, so the answer is going to depend on whether it caches, but the nice thing is that it returns false. Okay, now let's make things dynamic. Right, so all I've done is throw away type inversion. I'm saying I'm being lazy, just do the same thing you did before, but now I'm not bothering with types. What does it do? Returns true. So what happens is it says, well, I'm going to use the runtime type of this to figure out what to do. And in runtime, this is an integer, so it's going to use integer equality because that's overloaded in C#, and then figures out that those are equal. All right, here's a getter that gives me a T. Here's 5 that you can either you can get a string out of it or an integer out of it, depending on what you want. Here we say getter int, and normally this is more direct, but right here this equals new 5. And then this prints the integer we get. What does this do? This is the obvious answer. It prints 5. Well, the number 5. Okay. So now I make things dynamic. What does it do? So now it's being gradually typed. So doing all this at runtime. What? Returns 5. Okay, there's one vote. I'm going to get lots of votes. So who says returns 5? All right, or this is the word 5, sorry. All right, who says it returns the number 5? No, everyone's like, Ross is tricking us. I know he's doing it, so it must not be that.
Well, is it inferring that WriteLine generally takes a string, so it's just doing the dumbest thing possible?
You can think about that, but actually what it does is it crashes.
Oh.
It says, well, hey, this thing has 2 get methods. I don't know which one to call, so I'm just going to crash. I'm going to do one really other quick example. Here's one that snocks onto a list, right? So snock just adds to the end of a list. Well, it makes a new list and adds to the end of it. So I snock hello 5, I get hello 5. Now what happens if I make it dynamic? Any guesses? Crashes, correct. Anybody know why? No, okay. What happens is it says, well, toList, I don't know what that is. I can't figure that out. You're like, well, it worked before. Why couldn't you figure it out now? Oh, it's an extension method. It uses the static type information at compile time to figure out what it actually should be. Okay, well, let's just help that out. Okay, so you're supposed to do a numeral toList. We got rid of the extension method. Now what does it do? Now you're like all scared of your compilers and okay, well, it crashes. So what happens is toList is a generic method. And before it was using, or snock essentially was generic itself, so it figured out, hey, the common type here is object. But now we're doing this all dynamically. So it's saying, hey, we'll start as a list of strings. So I'm just going to guess, or as an enumerable of strings, so I'm going to just guess that I should be returning a list of strings. And then it gets to here and says, oh, let's add a number to it. Wait, I have a list of strings. Can't do that, crash. Okay, so to conclude, even though this is all still being like done, but we're going to exploit humanity in design, right? We can say languages are hard to do. Everything is undecidable. Everything has all these crazy problems. So let's look at how people use them, right? All these features are useful, but they're generally just done in the sort of most direct way possible, which is just too general, right? We're not using the full expressiveness of our language. So by analyzing how we use our languages, right, how the human behavior involved, we can come up with solutions that both are principled, right? They're decidable, things like that, or they don't have all that crazy behavior you saw in the previous slides, and they're usable, right? Because we analyze your behavior, we're going to use them the way that you wanted to. And that's what I do. So I think I'm out of time.
Yeah, well, we could take one question.
It's fine if everyone's exhausted. Oh, there's one.
Have you considered applying your analysis to a corpus of Scala code or a corpus of Martin Ordersky's code?
Well, Scala, so I've considered doing it. I'm trying to figure out how to deal with like all the other features it has. So I do know that a Scala researcher has a counterexample because what they do is they have list extend sort of maybe, actually I can do the practical example that comes up. A tree extends list of tree. Right? A tree is just a list of trees. And that's perfectly fine. So that's actually the example that came up in the Ceylon code. And that's essentially the example that came up in the Scala code as well, that we know of. And so it's possible, you could say, well, okay, just don't use this. The other option is to say, well, it's really easy. You just make tree now have a method or have a field that's a list of tree. And you lost some expressiveness, right? You no longer have that enumerable of tree as an enumerable of a list of tree. But you still have a fair amount of expressiveness. So it's a question of whether the trade-offs are worth it, and that's your choice is what to do. As I said, I don't make the choices. I have to argue really hard if I think something's broken and needs to be fixed. Anything else?
I think we're just about out of time, so let's thank the speaker.
All right, I studied used to make video games, so I actually worked on Activision's internal programming language that they use to script their games. And this was as an intern, but then they hired me back later on to redesign their language. Later on, I did some research on language design, and the Ceylon team contacted me about how they can apply that research to their language. And then the Kotlin team did the same thing. And just recently, like very recently, I started working with the Java team, but we haven't actually got anything done yet. So I'm working on bridging this gap between academia and industry, trying to help these people understand what research there is out there they can use, and also help the academics understand what the needs of industry are. So my goal in all this is to sort of make the industry languages better. Now, what's important to note is that I'm not saying make a industry language better. I don't have my own language. I actually want to make sort of many of them better. And also, better is in quotes. That's because it's not clear what better means. Right? We don't really have a good way to evaluate things like productivity or stuff like that. And although I used to be a web developer, did so before JavaScript was a really big thing. So I keep myself in touch, but this is something different between both uses of variance, or variance, concepts variance. The top is best represented using declaration site variance. That is, when you declare iterator, from this declaration, you can see that it has this property, because you can only get these values out of it. And the bottom is a use site variance. It's not a property of all lists, it's a property of how you're using this particular list. So wildcards encode use site variance. But in C# later, it started using declaration site variance. And from this experience, people have sort of said that this one is, if you can only have one of these two, this is the one to use. It's just, this one has a lot of syntax, and it can be overburdensome, whereas this one is easier for people to learn. So the Kotlin people wanted to use this, but they needed to interact with Java, and use site variance is more expressive than declaration site variance. And the thing to note also is that both of these are useful. They cover different kinds of situations, so ideally we could have both. So the question that came up was basically, how do we combine these kinds of variants? So let's give it a little more detail. So predictability isn't a mathematical property of languages, right? I can't formalize this in any mathematical way. This is a human property. This is about how people work with languages. And so this is something that I'm trying to see how we can bring sort of into mathematics. So can I try to abstract these things and say, okay, this pattern tends to be more predictable, or this behavior helps things out. And let me give you an example. So the Kotlin team, back when, was like, Ross, we want to be interoperable with Java, but we don't like wildcards. And I imagine a number of you can agree with that sentiment. But wildcards have a use. They encode something called variance, and variance is very prevalent across our programs. So what is variance? Well, an example is an iterator of integers can safely be used as an iterator of numbers, right? If I'm getting numbers out of it, I don't mind if those happen to all be integers. That's fine. It's just a coincidence. Another example is I'm only putting things into this list, and so I don't have to worry about whether that's a list of integers or a list of numbers or a list of objects. Any of those is fine so long as they can put integers into it. So these are I kind of want to learn something about the audience. Who here does some language design? Handful of people. All right. Any of you not like have a PhD? Sorry, of the language designers. Yes, actually, I want to know that too. So that's good to hit those hands. But of the language designers, who doesn't have a PhD? Oh, almost everyone. That's surprising. All right. Good to know. And now I know how much industry people there's in the audience. Okay. I am Ross Tate. I'm a professor at Cornell University. I also advise multiple languages on sort of how to improve their type systems. This is somewhat of an unusual setup, so I figured I should give some background. Okay, so first of all, I went to Cal San Luis Obispo as an undergrad. This is a completely industry-oriented school. I am, I think, the only person in my major that went to grad school my year. So I never planned on going to grad school. I used to make video games, so, but then I went to UC San Diego because of a bunch of pressure from faculty, and then interned at Microsoft Research, and then now I'm a professor at Cornell. Doing things every day and doing things just once in a while to keep yourself up to date. So rather than me making the call, I work with other people and help them, or who make the call and help them work that through. So my approach is to help industry language designers create the language that they envision, right? If you want your language to look like this, or act like this, or interact like this, you have an idea of how to go about doing that, but there's a lot of details to work out. There's a lot of technologies you have to introduce. There's just a lot of open problems. And so I help them navigate either the open problem, or either the existing problems and let them know what solutions exist already, or the open problems and come up with new solutions for them. So I just said I don't push my own vision, but I have this one principle I've seen sort of hold throughout all my interactions, which is this idea of predictability. So predictability is the ability for a program, or is the degree to which a programmer can predict what their language will do. This is something like, I can predict what if this type of code I'm going to write is going to type check. Or I can predict if this library I'm going to use is going to be usable. Or I can predict if this part of my code is going to perform well. If things go better than your predictions, that's great, but you at least want to know sort of the minimum ground so you can plan ahead.